in your course, and I welcome all the students. So students, today I'm going to discuss, I want to give you an overview, basic overview of what are the contemporary advancements in the field of soil. I'm basically a soil scientist, and my research area is development and application of cost-effective sensors and developing new application in the field of soil and crop using different types of AI/ML algorithms. So I am from Agricultural and Food Engineering Department, and in this lecture I'm going to talk about some basic overview of I want to give you some basic overview of different types of sensors which you use for advanced monitoring of soil. Apart from that, some of the applications which we have developed and scientists from all over the world have developed. So let us start. Um, you have to understand that soil, it is an important natural resource, but it is at the same time very undervalued natural resource. When you talk about uh, you know uh, natural resource, we generally talk about the uh, petroleum, coal, but we never talk about soil. We always try to neglect the soil because we cannot see as such any value for soil. But at the same time, you should understand that without soil, nothing is possible in this world. So although it is undervalued or neglected, we should give proper importance for soil, because for developing 1 inch of soil, it takes millions and millions of years, but it takes a couple of seconds to destroy it. And if you destroy your soil, you can have very devastating consequence. So generally in the soil, if you take a vertical section, you will see different types of horizons. Uh, Starting from O horizon, then A horizon, then B horizon, then C horizon, R horizon. So these are different types of layers which are formed due to different types of chemical and as well as physical processes. And if we talk about the function of soil, of course, it is a medium for crop production. It is a filter. It is a filter for different types of water and wastes. It absorbs different types of gases. It is a home of all the macro and microorganisms. This is the medium for plant growth. It is a waste decomposer, and at the same time, it is source material for construction, art, medicines, and it gives you the snapshot of geological, climate, biological, and human history. And at the same time, it is an essential natural resource also. So without soil, nothing is possible in this world. If you also talk about from the engineering point of view also, you build all the structures, all the engineering construction over the soil, and if soil is not having the enough strength, you cannot build it. So if you take the composition, if you discuss the composition of the soil, soil is basically composed of both you can see that half of the soil volume is composed of solid part and half of it is composed of air and water. And among these solid part, there are both inorganic components as well as organic matter. Inorganic component can be divided into different fractions based on their size. And organic matter is also very important for soil because that takes care about soil chemical and biological activities as well as the physical activities. Without the presence of soil organic matter, it is not possible to maintain a good healthy soil. And when you talk about a good healthy soil, that takes care of all the crop production issues as well as for maintaining the normal ecological balances. So soil organic matter is a very important component of the soil, but I'm not going to discuss these things in details. I'm just giving you some overview. Now remember that whenever we want to grow some crops over the, we are dependent on soil because whatever we eat, they are being grown in the soil. And just like when we have some problems, we generally visit our doctor. Doctor prescribe us some tests before giving us the recommendation or prescription. Similarly, for growing any crop, you need to know if your soil is having all the nutrients which are required by the plants or not. So, to identify whether the nutrients which are required by the plants is contained in the soil in optimum amount, we need to go for soil testing. Now, soil testing, the general concept of soil testing all over the world basically depends on the traditional lengthy laboratory chemistry experiments. So we generally take the soil and then we digest it, we do different types of chemical analysis, and after that we quantify the different components which are present in the soil, and based on that we identify, okay, we are having this component in low quantity, this component in medium quantity, and this component in sufficient or high quantity, and based on that we give the farmers the fertilizer recommendation. That means you should apply this fertilizer to your field so that your crop can be grown optimally. So this is the traditional ways of soil testing. However, these traditional ways of soil testing has some downsides also. What are these downsides? First of all, it is very time consuming because you using these traditional methods, you cannot go beyond couple of 10 to 20 samples per day, and also these methods require consumables. This method is cost intensive, and also we have millions and millions of farmers in our country and a handful of soil testing lab. We have in our country only 4,000 soil testing lab. So 4,000 soil testing lab cannot cater the needs of millions and millions of our farmers, because they will send them millions and millions of soil samples to be tested. So it is not at all sufficient to cater the needs of our farming community. As you can see, this is the traditional soil testing lab, and these are some traditional parameters. Just like when we go for COVID testing, generally prescribe us do some kind of testing or blood test. So these are some of these parameters in soil which we require to maintain for maintaining the good crop growth and to maintain their yield. Now, what are the importance of unconventional methods? So you know that there are 140 million land holdings in India, as I have just mentioned, with an average size of just above 1 hectare, which is 1.115 hectare. And 2/3 of these land holdings are marginal, which are less than 1 hectare of land with an average size of 0.39 hectare. So we have only 3,887 soil testing labs across India, and analyzing capacity of the soil testing labs simply lags far behind the requirement. So that is why Government of India in the year 2015, they have started a soil health card scheme where a prescription for the soil will be given to all the farmers. But the problem is that was able to sensitize the farmers, but problem is the number of samples which are required to give the proper and accurate estimation of fertilizer and prescription is not possible in Indian context. So we have to bring new technologies and practices to a large number of smallholders scattered over a vast countryside and integrating them with the modern inputs and output market, and which is of course a huge challenge for Indian agriculture. And of course, if we think about some unconventional sensor, that these are smart and cost-effective soil sensors that can realize the digital India and also can encourage agri startups also. So this slide shows why advanced soil sensors are needed in India for soil mapping. For example, you know that when we apply the fertilizers generally boost agricultural productivity. But so farmers generally believe that if a little of fertilizer is good, then a lot will be better, because they do not have the access of traditional soil testing. Okay, so what they do without soil testing, they apply the fertilizer in a blanket fashion. And when they apply the fertilizer in a blanket fashion without seeing the spatial variability of the soil properties, and the consequence will be loss of inputs because they are also applying the fertilizer in that spot where there has been already sufficient amount of nutrient. So they are basically losing the inputs, they are losing the natural soil fertility, because if you continue to apply this type of fertilizer these are synthetic fertilizer. So when you apply for long duration of time to a field, this field also loses the natural soil fertility, and also this excess amount of this fertilizer can go to the groundwater and can create human health hazard. So to stop this fertilizer application without soil testing, we use sensors to assess the soil health. And of course, in these sensors, there are different types of cost-effective proximal soil sensors and remote soil sensors. And we use artificial intelligence and machine learning in combination with the sensor signal to map the soil properties. So the objectives are three types. One is on-site rapid testing, second is cost-effective soil testing, third is minimum soil processing. So ultimate our goal is higher nutrient use efficiency, higher crop productivity, and ultimately higher profit. Because if you cannot give the profit to our farmers, they will not be interested to adopt these new advanced sensor technologies. So I'm going to talk about some advanced sensors today, starting from portable XRF, then diffuse reflectance spectroscopy, then some smartphone image sensors, and how they are nowadays advancing this discipline of soil mapping we are also going to discuss. But before that, we should understand that this is the conceptual framework of this whole site specific nutrient management. So we have the access of mobile soil testing lab. We have on the go soil sensor, which we can drag in the soil and then and there predict the soil properties. We have this portable XRF, we have the spectral sensor, we have smartphone images, we have other optical sensors, cheap optical sensors. So when we have all these different types of sensors, then we can use them to produce the yield map of properties, yield map of crop. You can see this is the yield map showing the spatial variability of
Excuse me, sir.
different yield properties. Yes.
Sir, the slides are not visible.
Slides are not visible.
Yes, sir. The slides went off.
Okay.
I think you can reshare the screen again.
All right. Is it visible now?
Yes.
Okay. So what happens? This is the smart soil sensing framework. So you can see this is we are ultimately creating the yield map using all these different resources: mobile soil testing lab, on the go soil sensors, portable XRF, spectral sensors, smartphone images, optical sensors, and we are producing the yield map. This yield map will be considered as an input in the final decision making system. And here in this final decision making system, we are getting the inputs from different remote sensing platforms, also from smartphone images, and also from UAV images. We are taking some, and also some crop canopy sensors also. So based on this decision making system, we can develop a variable rate application so that judicious amount of inputs can be applied to different places of the soil to maintain the profitability, to maintain the environmental sustainability. So this is the basic conceptual framework of the smart soil sensing framework. And for this, we are going to use, apart from these on the go soil sensors, we are going to use some amount of proximal soil sensors. So proximal soil sensors are those soil sensors which we generally use at a distance below 2 meters from the soil surface or at the adjacent soil surface. So there are different types of soil sensors. First category measure the reflected radiation. So diffuse reflectance spectroscopy, NICS Pro, camera, all these are the reflected, these are the proximal soil sensors, so they measure the reflected radiation. Measure, some of them measure the incoming radiation from soil like PXRF, gamma spectrometry, and LIBS or laser induced breakdown spectroscopy. Some measures backscattered electromagnetic waves or temporal propagation of electromagnetic waves like electromagnetic induction, GPR or ground penetrating radar, time domain reflectometry, frequency domain reflectometry. Some measured the strength, horizontal or vertical soil strength like penetrometer, and some measures the electrochemical properties like ion selective electrode, ion selective field effect transistor. So all these different types of proximal sensor are specific to some specific uses which we are going to discuss. Now let us start with the first one, that is called the portable X-ray fluorescence spectrometry. It is a handgun type of instrument, and we can, you can see the size, and it is a very small, handgun type of instrument, and you can carry this instrument in the field and can touch its nose to the surface of the soil and press the trigger. It will give you the reading of total elemental content of the soil within only 60 to 90 seconds. And using this total elemental content and some kind of calibration equation, you can predict different types of soil parameters, starting from soil pH, electrical conductivity, cation exchange capacity, phosphorus, potassium, calcium, magnesium, sulfur, micronutrients, gypsum percent base saturation, and so on, apart from heavy metals also. Because we have seen that if these elementals, which with the elements which we are getting from this instrument, graphical user interface, and they can be Bluetooth operated. So these these results can be transferred to a PDA, and from there we can develop, we can feed different equations to predict these soil properties, because these soil properties are dependent on these elemental contents. Now, what are the benefits of this instrument? This is very lightweight, only 1 kg of weight, and it can be, it is portable, so field portable. It requires no consumables like the traditional methods. It is non-destructive. That means if you have very small amount of sample, and in the traditional method during the digestion process the sample get lost, so in this method you are not destroying the sample, so it is a non-destructive method. And multi-elemental analysis, it is a high throughput, and it gives you the results of 20 to 30 elements within only 60 to 90 seconds. Can you imagine 60 to 90 seconds without any consumable, without any destruction of the sample, and you can use different types of calibration equation to predict soil properties. This instrument has different manufacturers, and this is off-the-shelf instrument, and this basically works on the principle of X-ray fluorescence. Now, this instrument can be used both in the field as well as in the laboratory. So this instrument is useful for both in situ determination. If you want to predict the soil properties on site, you can do it. At the same time, you can in the laboratory condition also, you can predict the soil properties. As you can see, scientists are using this instrument in Western countries directly in the field to measure the soil properties. Okay, so this instrument is regarding the elements it can measure. This instrument can measure elements from magnesium to uranium. So 20 to 30 elements between magnesium to uranium it can measure, and limit of detection is almost 1 ppm. Here you can see less than 5 ppm, but nowadays more advanced instruments are there which can measure up to 1 ppm of concentration of any element from magnesium to uranium. So if you see the evolution of PXRF, the evolution of PXRF, the first application of the PXRF started in 1980, where this instrument was used in geological estimation, geological parameter estimation, and then there are different versions of advancement, and ultimately we are now getting these advanced models which can be used in different metrics. Earlier, this instrument was used in geological application as well as in alloy industries for measurement of purity of the alloy, but nowadays we can use this for different matrices like soil, vegetation, and so on. So the application also has expanded and creates a paradigm shift in natural resource management. Now, if you talk about the reference methods, well, there are three reference methods. The first one is United States Environmental Protection Agency method 6200, and then United States Department of Agriculture. The second method, the third method was given by Soil Science Society of America, written by myself and Professor David Wendorf of Texas Tech University. Now, these three methods are known as the reference method, and in Western countries nowadays, this instrument is utilized as a standard method of soil testing, as a replacement of the traditional ways of wet chemistry based soil testing. Now, when I was doing my PhD back in 2008, we started thinking, let us use this instrument for heavy metal characterization in the soil. So at that time, this instrument was actually used in alloy industries. So we thought that if it can measure this heavy metal in the alloys, why it cannot measure that the heavy metals in the soil which are creating problems? So we went and then we collected several soil samples nearby the industrial sites of southern United States, and then we tried to measure the correlation between the standard reference measurement and our method. So we have developed several equations to correlate the concentration, standard concentration, and our PXRF based results, and we have seen that this is really useful for predicting most of the heavy metals. And also using another statistical approach called geostatistics, we have produced the spatial variability maps of these heavy metals nearby these industrial sites. So that was our first application. Then the new application evolved. So we started with the very basics like simple linear regression, multiple linear regression, and we tried to predict different types of soil properties, starting from electrical conductivity, which measures the soil salinity. Then we measured the soil pH, or soil acidity or alkalinity. Remember, all of these are mandatory soil testing parameters for soil crop production, and that is why the traditional methods are really time consuming, and we have seen that using these simple models we can create these calibration models for predicting these components within a very short period of time. We went to Eastern Europe, Romania, and we utilized our instrument directly in the soil to measure the heavy metals in the abandoned industrial sites from the Soviet era. And then we have created these contamination maps for this area, and we have executed different types of clustering like PCA, then K-means clustering, and different other types of clustering to cluster the soil for source zone identification. When you have this data, if you use different types of clustering, you can have you can define the source zone of those different types of heavy metals. You can see these are the spatial variability maps of soil properties or heavy metals called pollution in the studied region. We went to South Africa, and then we measured the tailing characteristics. South Africa is a home ground for different types of mining activities. So we went to we went and collected samples from different mining areas, and we predicted the elemental content in these mining areas using partial least squares regression, principal component regressions, and so on and so forth. And we have predicted these metals using different parameters like PXRF peaks and so on. And also with my Brazilian collaboration, we have mapped the soil parent material. Now you all know that we derive soil from rocks. Millions and millions years of different types of processes are required to convert a rock to soil. Now, if you identify what is its precursor rock or parent material, we can predict several things about that soil. So recently we have used this PXRF and also different types of deep learning methods like artificial neural network to predict the type of the soil parent material. Not only we have predicted the type of parent material, but also we have created the map of their distribution, so that we can infer what is going on in that particular soil. We have developed several equations using our portable XRF data, for using linear regression, polynomial regression, power regression, and stepwise MLR for predicting different elemental content on soil nutrient. You know that soil nutrient is that component that is taken by the plant to maintain their lives. So these exchangeable pot calcium, available phosphorus, these are soil nutrients, and these soil nutrients are being absorbed by the plants to maintain their life. And we have developed certain equations to predict the soil available nutrients also. We have developed certain equations. We have developed the rules to classify different types of carbonates which are present in the soil. Carbonates is an important component of the soil, and there are different types of carbonates like primary carbonates, secondary carbonates, and secondary carbonates can also be divided into, according to their age, into 6 different categories. So we have used some kind of rules by using the PXRF results, and we have developed these rules using if and then based rules, just like the decision tree or cubist model. At the same time, we have developed the we have applied the support vector regression or support vector class machine classification to classify different types of 6 different types of secondary carbonates. And then we have, this is, you can see the support vector machine boundary maps to define the distribution of different types of secondary carbonates in the soil. First Indian application, we did it in 2019, where we have collected soils from 3 different land use type of northern part of India. So we collected 500 different types of soil from agricultural site, from forest site, and from converted areas. Converted areas are those areas which were earlier agricultural sites, but 20 years back they slowly started converting into agricultural lands. So we tried to see whether using this PXRF data as well as different types of classification algorithm, we can classify the land use. Because in near future, if we can have any unknown sample, and if we fit in this model, if we can classify their land use, then we can predict so many things on that particular soil. So we have developed different types of classification algorithm like random forest, linear SVM, non-linear SVM, classification regression tree, and we got very high classification accuracy, as you can see from this confusion matrix and misclassification rate. The lowest misclassification rate we got from non-linear SVM, which shows the 7% misclassification rate. And at the same time, you can see their portable, these are the relative importance or random forest relative importance for the PXRF variables. We have arranged them based on their importance to classify the soil types. Apart from that, we have developed the decision tree rules for developing for classifying any unknown samples to one of these 3 categories, and this is the cart tree construction. Not only in the soil, but also we have extended this application for plant, because the plant can accumulate different types of metals, and using those equations you can predict different what is the elemental concentration within this plant property. And also we have measured the the water heavy metal content, and whatever we have discussed so far, all these were published in very high good impact factor journals like Geoderma Computers and Electronics in Agriculture, as well as Geoderma Regional and Journal of Hydrology. So nowadays in Western countries, they have already utilized this technique for characterizing their soil, and now here in India we are trying to adapt this technology. We are trying to convince our farmers or the farming input providers to use this technology for producing the cost-effective prediction of soil properties and giving them the prescription for their soil. Apart from that, there is another technology in which I worked, This was actually my topic of my PhD. So diffuse reflectance spectroscopy. So it is also a very fast technology. It is faster than PXRF. It takes only 5 seconds. So it is a kind of, it depends on the reflectance from the soil. So basically you have a, this is the spectroradiometer. So this spectroradiometer, you can carry it in a backpack, and you can carry it in the field. It is portable with a handheld probe, and using this handheld probe you can scan any soil samples, and the reflected energy can be collected using this probe, and then using the total internal deflection, it will go to the spectroradiometer, and from this spectroradiometer we can transfer this to any PDA, and in this PDA we can do different types of signal processing or spectral processing, and after this spectral processing we can use this process spectra for developing different types of chemometric models. So this is also very fast, cost effective, with almost zero recurring cost. It requires minimal or no sample pretreatments. It is high throughput and non-invasive, and also portable. And there are different types of parameters you can use, predict, like organic carbon, available nitrogen, phosphorus, potassium, pH, clay, moisture, heavy metals. All these are very important soil properties for the growth of the plant. So here you can see a couple of examples where this instrument has been utilized for measurement, accurate measurement of different soil properties. This is for the organic carbon, and people have used it for inorganic carbon, clay. I'm not going to discuss all those details because our time is limited, but just to give you an idea about this instrument. Now, once we have this instrument, we have to go through different types of spectral pre-processing. So these are the raw soil spectra. After we get the raw soil spectra, we can develop the seamless spectra, then we can smooth the spectra. And then after the smoothing the spectra, we can do different types of further spectral pre-processing, like taking the first derivative, taking the second derivative. We can do Fourier transform. We can do different types of gap segment derivative. And also we can do different types of wavelet analysis. You know about the wavelet analysis, so I'm not going to discuss this further. So after this wavelet transform, we can take the wavelet at particular scale, and then we fit them using as the predictor for soil properties. One of the example you can see, this is a noise corrupted spectra, and after we get this noise corrupted spectra, we did some Haar wavelet transform. After we did the Haar wavelet transform, we did some thresholding. Now for thresholding, we selectively removed this noise, and then subsequently we did the inverse Haar reconstruction to get the noise removed spectra. So this is the original noise corrupted spectra, and you can see after the inverse Haar reconstruction, we get the original the spectra after the noise removal. So using this type of wavelet analysis, we can do different type of spectral processing, and after the spectral processing, we can combine these the reflectance values with stepwise multiple linear regression, partial least squares regression, principal component regression, penalized spline, random forest, support vector machine, artificial neural network, and many more. And we can do also different types of clustering analysis also to predict certain soil properties. One of my student has developed a variable indicator from this spectral variables. So once we take the soil samples from a area, we can take the scan, and after we take the scan, we can go with the full spectrum analysis. You can see here we are fitting the full spectrum PLSR model using the 350 nanometer to 2500 nanometer range, because this instrument uses the 350 nanometer range to 2500 nanometer range, that is visible to near infrared range. So using the full spectrum, they have developed the partial least squares regression. But here we have developed another variable indicator suite, so that we can get more easy model or less complex model. So we call it the variable indicator suite. And for the, there are different types of indicators in the variable indicator suite, and we selected the handful number of samples wavelength, and then we fitted the support vector regression, and then we have seen that support vector regression using the handful of wavelengths instead of the whole wavelength range will produce the best approach. And then we have integrated it with the kriging for producing the spatial map of soil properties. I hope that you all know about geostatistics since you are dealing with this earth science. So this kriging will help you to map these soil properties and give you the spatial map of soil properties. So these maps were created in Romania and also in Hungary. So so here you can see these maps were created originally in Romania. So these are the actual output maps. So this is the map of sand concentration and then clay percentage and silt percentage, total nitrogen, total carbon, and Lawson ignition method. And you can see clearly see the spatial variability of the soil properties, from one location to another location. And that shows the utility of this technique for identification of variable soil properties. Now, back in 2014, we thought that, me and Professor Wendell, we thought that, okay, we have seen that these two sensors, PXRF as well as DRS, are very good and they can be utilized in isolation to predict certain soil properties. What if we fuse the data set together? So we call it a sensor fusion technology. So here we have seen that if we fuse the data set of these two different sensors together, we can get better accuracy of soil prediction. So you can see here it is called a sensor fusion, and we are getting synergistic results of 2 plus 2 equal to 5, and we got a US patent for this invention. So we use this US patent and we showed that we can predict different soil properties with higher accuracy than using these two sensors alone. So this is called sensor fusion. Also, we use this sensor fusion to predict the soil salinity. So we sampled the soil from highly saline lakes and we fitted the soil salinity using the spectral responses using support vector regression, and we got very high good R square of 0.95. We supported our results using the electron microscopic result also. Recently, we have started applying another small sensor which is Bluetooth operated, and so this is called Nix Pro color sensor. So this Nix Pro color sensor is rechargeable and portable, and it has got their own LED sensors. So it can be connected and operated through Bluetooth, and it can capture the color of any surface, and we have utilized this for color of the soil. And the color of the soil can be connected to several soil properties. So we utilize this technology to rapidly predict several soil properties using the extracted color. So here you can see the scientists have used this sensor to capture the color of the soil, and using the cloud computing, they have uploaded the data directly from the app to the server, to the cloud server, and did some calculation and then predicted different soil properties for rapid mapping, on-site mapping of the soil properties using the Nix Pro color sensor. So this sensor is really helpful for real-time soil mapping. Also, this sensor has been utilized for replacing the traditional qualitative method of soil color description. So the traditional qualitative soil color description was based on certain books called Munsell soil color books, and we have proved that yes, it is now possible to use this sensor to quantitatively predict the soil color using some artificial neural network and higher deep learning models. So you can see we are comparing the kappa coefficient and accuracy terms using different types of deep learning models, and so that shows that how these new advanced sensors but cheap sensors are useful for predicting different types of soil properties. One of my PhD student has fused this diffuse reflectance spectroscopy and Nix together using another approach of sensor fusion, and she has proved that when we fuse this data set together, we can get higher accuracy for prediction of soil organic carbon, which is an important property of soil. So using this, we can get higher prediction accuracy by sensor fusion using this combined data set from Nix and DRS. So this is called sensor fusion. There are many methods of sensor fusion. Here I'm just giving you some 1 or 2, 3 examples. You can go ahead and see how to fuse the sensor using novel sensor based methods. There are at least 5 to 6 different methods to fuse the sensor data. Also, we have tried to fuse the data of NICS, PXRF, DRS in combination of different machine learning approaches like random forest, like support vector regression, like and also some deep learning methods also. And we tried to see whether this combination of these different data set will give you basic, better understanding of the soil process or not. You can see here we are combining here PXRF, then DRS, then NICS together, and we have seen that when we combine this data set together, it is giving us very accurate result for predicting different types of soil properties. Recently, we have also used this USV microscope. This is available in Amazon and Flipkart. You can directly plug it, and then you can take high resolution images of soil, and then you can do several types of image processing, histogram equalization, and then you can feed this process image directly to CNN to predict certain soil properties. We have utilized this for prediction of soil organic carbon, and we got very high R square values for predicting. People are developing the cheaper versions of low cost portable spectrometers, and using these cheaper spectrometers, you can see they are now so different scientist groups are predicting different soil and plant properties nowadays. Our students in my lab at Agriculture and Food Engineering department are developing these cheaper indigenous sensors, and these are very cheap, and you can utilize this setup to you can develop this setup within only 2000 rupees, and you can utilize this for capturing the images, hyperspectral images, and then utilizing these hyperspectral images you can predict several soil properties. So this is the different types of vision spectrophotometer we have developed, and now we are predicting the organic carbon using these spectrophotometer or spectrometer results. Also, we are using the we have used the machine learning approach to develop this portable soil moisture sensor. This is acoustic soil moisture sensor. So here there is an speaker, and there is a receiver, and in between we are packing the soil, and the acoustic sound we are generating, this speaker is generating at a specific frequency, and the time it takes to reach the source to the receiver, it will vary based on the moisture content of the soil, and based on this variation of time of flight, we have calibrated the moisture of the soil, so using the velocity of the sound. So it is an acoustic soil moisture sensor, and we have used a mixed linear mixed model to develop different types of calibration equation based on soil texture. We have also utilized this mobile image based soil recognition. These sensor assembly you can get it from Amazon or Flipkart, very cheap, 100 to 200 rupees, and you can generally attach it with your mobile phone, and you can take high resolution image of your soil, and using this high resolution image you can extract certain features from those images, and after extracting the features, if you go ahead with the principal component analysis or different types of clustering methods, you can cluster different types of soil. We have recently proved its utility for separating or clustering different types of soil, and so that is one of the new application in sensor based soil property prediction. We have developed this new setup for capturing the mobile image by this is the black box which we have created, and this is custom made, which is lined by these LED sensors, LED arrays, and we are taking the image at different illumination intensity, and we have captured this image using the smartphone. This image has been directly fed into the convolutional neural network, and we simultaneously we did some spectral pre-processing also. Like once we collect this RGB image, we convert it to the grayscale image, and from this grayscale image we have used the scale invariant feature transform to develop these local feature descriptors, and then we did some k-means clustering to develop a dictionary of shift features or scale invariant feature transform using the bag of visual words model. This bag of visual words model is used in NLP, and nowadays we have used this for soil image processing also. So bag of visual words we have used to create this shift histogram. Simultaneously, we have developed this textural feature, extracted these textural features, and then we have collected these local binary patterns, heraldic features, grayscale features, HSV features, and we have combined them together in the global features. And then we have predicted the soil properties using random forest. So you can see using this, both these deep learning method as well as machine learning method, we have predicted the soil properties with high, high accuracy, and that shows the importance of this, smartphone-based future characterization of the soil properties. Not only that, we have also developed a mobile app for taking the images from the farmer's field, or directly they can select the image from their gallery, and then they can upload this data into the server. So we have fitted the model, and we have hosted that model in a Flask server, and that server we have kept in the cloud platform, cloud storage platform. And using this cloud storage platform and this fitted model and the server, we are now able to capture that, we are now able to get the results of the soil properties very easily. So once we upload this into the server, it will return us the values, and then we can directly send these values to the farmers' mobiles, because we understand that this is the future of Indian agriculture, because nowadays most of our farmers have the access of mobile phone, but in coming years they will be also having the access of smartphone. So without having to depending on the traditional methods of soil testing, if they can get their soil test values directly in their mobile phone with a click, that will boost their confidence, and that will boost the the profitability of the farmers also. We have also developed different types of image processing techniques, because in the real field situation, one of the major problem is variable illumination intensity. So to remove this variable illumination intensity, we have developed a methodology where original image will be passed through the high-pass filters, and then we'll keep only the reflectance image and remove the variable illumination. And after we keep the reflectance image, we'll do the segmentation, and then image normalization and k-means clustering, and then we'll extract different types of color features in different color space model, and using these color features we'll fit different types of model. At the same time, to see the model robustness also, we added noise and part of the image to see how our model behaves when there is some noise. So after we extracted these features, we have developed these model stacking. So in this model stacking, you can see there are two types of model, level 0 model and level 1 model. And in one, we have used this process data from this color space model, absolute maximum scalar, and this standard scalar. So you can see here we have fitted random forest and support vector regression with RBF function, radial basis function, and ridge regression. This is one way. Another way, random forest and linear SVR with the AdaBoost regression, and then we predicted the organic matter. So this is called tree-based pipeline optimization tool. So we have optimized this result for predicting the soil properties in difficult condition, because when you take the image from the morning, the illumination will be different. When you take the image in the evening, the illumination will be different because of sunlight variation. So that impacts the model accuracy. To remove that model accuracy, we have developed these image processing in combination with this machine learning stacking strategy. Different other researchers also across the world are developing new strategies for smartphone based soil testing. This is one example, using artificial intelligence and machine learning. And so apart from this convolutional neural method, the normal convolutional neural methods, we are extensively using different types of deep learning architecture for image processing, like VGC16, ResNet 50, Exception, and then recently we have also used the Vision Transformer also. So apart from that, smartphones are being used for rapid soil testing. They have got these disposable electrodes. So if you put a drop of any liquid from the soil extract, that will be transformed into the smartphone using the Bluetooth, and then using the cyclic voltammetry, we can measure different types of soil properties. Also, using the smartphone, you can use it as a colorimeter to predict the soil properties also. You can use your mobile as a arsenic detection tool also by detecting the color change and using different types of model. Recently, a model has been developed. This prototype has been developed by combining the smartphone and this USB microscope together, and they call it KenkaNet, which is an artificial neural network based object detection smartphone application, and mobile microscope as a point of care diagnostic aid for soil transmitted helminthisis or diseases. So nowadays they have used this for identification of the soil borne pathogen also. IBM technology has developed this agropad technology, where you put the soil extract in this pad, and it will develop some color changes, and using an app you can capture this color change, and it will calibrate and it will basically give you the reading of different types of soil properties. So it is an recent advancement. And FarmBot is an open source precision agriculture farming project which consists of a Cartesian coordinate robot, farming machine software, and documentation, including a farming data repository. It helps for the owner to end-to-end farming by himself, ranging from seed plantation to weed detection and soil testing to watering of the plants. So this is an advancement of AI/ML in the soil. And also nowadays we are using extensively for satellite for soil quality assessment and mapping. As you can see, we are using both multispectral remote sensing as well as hyperspectral remote sensing. Of course, hyperspectral remote sensing gives you more high resolution data than multispectral remote sensing and panchromatic remote sensing. And using this, you can predict different types of soil properties. So here you can see different types of hyperspectral remote sensing platform like EO1 Hyperion imaging spectrometer, and using EO1 Hyperion spectrometer, you can predict the soil properties at greater resolution. So here another advanced airborne hyperspectral remote sensing sensor called Aviris NG, Aviris new generation, which scientists have used for predicting soil properties with greater resolution. So it produces the calibrated image cubes, and it helps for developing the high resolution soil maps. So this airborne hyperspectral remote sensing platform has been flown to around 82 different areas across India, which was operated by ISRO. They brought this this Aviris sensor from NASA. And then they flew it over the several spots over India, and then they acquired these images. And after acquiring the images, they have analyzed these images for high resolution soil mapping. It is a whisk broom sensor, and using this whisk broom sensor, we are getting high resolution data cubes for doing more high resolution soil image analysis. So of course in India also, they have sent this HISIS sensor satellite in 2018 to capture high resolution images, hyperspectral images. And using these high resolution hyperspectral images, nowadays we are able to predict the soil properties in a greater resolution. Apart from this hyperspectral remote sensing, hyperspectral imaging is also advancing nowadays. We are taking the hyperspectral images from the scanning system. Using this hyperspectral scanning system, we can develop these hyperspectral images data cubes. And after doing the normal soil sampling analysis in the laboratory, we can combine these results together with different types of machine learning techniques like PLSR, artificial neural network, QBeast, extreme learning machine, convolutional neural network, then K nearest neighbor, Mars, random forest, XGBoost, you name it. And you can predict the soil map. You can develop the soil map at different, for total nitrogen, available nitrogen, ammonium nitrogen, nitrate nitrogen, microbial biomass nitrogen, and so on. And also hyperspectral imaging has been used with different types of other machine learning, properties also, machine learning models also, for predicting different types of soil total nitrogen also. So these are some of the examples. UAVs have been extensively used nowadays, using different types of sensors like thermal sensors, visible RGB sensor, multispectral sensor, hyperspectral sensors, and we are using these UAV images for doing different types of operation. One recent operation, you can see it has published in 2018. So they are flying, they are flying these DJI Phantom 4 Pro and then capturing the image of the soil. After capturing the image of the soil, they are using these augmented reality glass. So to communicate these developed mapping strategy to this augmented reality glass, and a operator can wear this glass and go to the field and capture the proper soil samples for subsequent mapping. So this is an advancement of drone and augmented reality based soil sampling and mapping. IoTs have been extensively used in soil. You can see this is a block diagram of smart farming system where they are using the temperature, pH range and water level to develop this type of different types of soil properties. And digital soil mapping is another advanced method of soil properties, advanced method of soil mapping, where we are using the original soil data along with the covariate data, digitally available covariate data, and we are combining them together using AI/ML tools like RF, random forest, artificial neural network, QBeast, CART, SVM, to produce the high resolution maps at different depths. You can see this is a sand content map of western part of our country, which is created by digital soil mapping. So this is the digital soil mapping data flow, where we are using different source data from UAVs, from satellite, and then we are combining with the normal soil data in using different types of approaches like advanced regression modeling, and then geostatistical interpolation like variogram modeling, to get ultimately this type of results where we can have higher resolution spatial variability maps of soil properties. So these are the last couple of slides. So here you can see that digital soil mapping can be utilized to get the huge amount of database which have been already gathered by different organizations of the world. And specifically the soil health card program by Government of India has developed crores and crores of data, and if we utilize this huge amount of data from the soil health card, that will be a big data, and we can do some big data analysis using the available infrastructure, and we can create a soil fertility map across India using different IoT platforms, cloud computing, and advanced machine learning and deep learning models. So this is the final slide, guys. What we envision as a soil scientist is that there will be a lab in a box soil testing protocol where we will have the access of all these individual sensors. All these individual sensors are specific to a specific set of properties like portable XRF, NICS Pro color sensor, smartphone images. There are the different multiplex devices, and all of them will be combined together to a mobile app for on-site soil fertilizer recommendation. We call it a soil test expert system, where all these complementary data set will be fed, and then using the artificial neural network or any other advanced machine learning or deep learning methods, we can predict the fertilizer for rapid on-site monitoring of soil properties. So in conclusion, I can say that AI has the potential to analyze and monitor soil health, which helps to improve the sustainability of a given piece of arable land, and it saves the resources of labor and the time for farmers. IoT helps farmers to monitor and improve the productivity of the soil as well as crop, and remote sensing technology helps in mapping land use, land cover changes, vegetation indices, also in predicting crop yield, and drone play an important role in precision farming like in soil mapping, vegetation indices. And of course, we will all agree that AI is a game-changing tool as far as the modern agriculture is concerned. So thank you, guys. Thank you. I wrap up. This is the end of this presentation, and I'll be happy to take any questions if you have.